Okay, so in the last video we left off talking about how to solve, using differential equations, solve for either velocity or time, um, a velocity-dependent net force situation. In this case, there was only one force in the net force equation, and that was the drag force. So F net equaled the drag force. But what about if something is free falling and you have a force of gravity in addition to a drag force? So let's check that out next. In this case, we're just going to solve for velocity. You could rearrange for time if necessary, but we won't do that for the sake of time. Alright, so the situation is something is falling and it's got gravity acting on it, and it has a force of air drag, air resistance, that is again dependent upon velocity. And so just thinking about it, when you start off, if you just drop something from high up in the air, if the air drag is proportional to, let's use B instead of K this time. If the air drag force is proportional to velocity, when you first drop it, its speed is 0. So this is 0. This force is 0, so it only has gravity acting on it. But immediately after it picks up a little tiny bit of speed, like a speed of 0.00000001, then it has a tiny force of air resistance acting up, trying to slow it down, and gravity is still pulling down with the same force because the mass isn't changing, and we're assuming we're relatively, close to the planet, so that the acceleration due to gravity doesn't change appreciably. And so as this thing speeds up, the force of air resistance gets higher and higher. But what happens, let's just think about it before we actually solve it. What happens when the force of air resistance equals gravity? Is that going to keep getting bigger? And in that sense, is that going to slow down the object, kind of like a parachute? And if you want to keep going even farther, is that going to slow it down, stop it, and turn it around, and it's going to start flying back up into the air? That's not going to happen, no. What happens is it reaches a terminal velocity, so once the force of air resistance equals the force of gravity, it stays that way, they stay equal, and you can move at a constant speed because your net force is 0, you have no acceleration, and you just fall at what's called terminal velocity. But let's not take our word for it, let's actually solve for it. So this is kind of a free body diagram, although this force is changing over time. So let's just do a net force equation. We got F net equals, let's just call down positive, just for the fun of it. And here we have, I feel like Bob Ross, here we have a happy little positive arrow going down. So that's going to be mass times acceleration due to gravity, pulling down, minus the air resistance force going up, B times V. In the last problem I used K as a constant. It doesn't really matter. Just pick a letter that you like, maybe the first letter of your name, and go with it. And of course, net force, as we know, is mass times net acceleration, mg minus bv. And of course, acceleration is the derivative of velocity. So very quickly, we get to where we were in the last situation, where we have m dv dt equals the constant of the drag coefficient times velocity. And notice both cases this air resistance force is negative, meaning it's trying to oppose its direction of motion. Alright. And from here we can let's just divide both sides by m. m. So we get dv dt equals, the m's cancel here, g minus b over m v. Then what we can do is multiply both sides by dt, kind of that faux algebra. I don't even know. I just made that up. That's stupid. Kind of that faux algebra that I was doing there. Yeah. Divide both sides by dt. Sorry, multiply both sides by dt. dt. Divide both of those cancel. Divide both sides by g minus b over m v. And what that turns into is 1 over g minus b over m v dv equals dt. So now we're going to integrate both sides. And this time, last time we integrated, I did it for you with a definite integral, meaning like, again, I apologize if you haven't taken calculus yet. If any of the calculus stuff that I kind of skip over baffles you because you haven't seen it yet, ask me and I can try to go into more detail. But I am skipping over some basic calculus stuff, just showing you the actual steps. So some of this might be like, what's going on? Anyway, here I'm going to do an indefinite integral, and you'll see a slight difference because of that. But this is kind of crazy. There's no like, we want to integrate with respect to v here, but there's all this other g minus stuff. And if you've taken calculus, you know that that's not simple. So what is usually done in this case is you do what's called a u substitution, where you substitute all this for u, because we know the integral of 1 over u would be like ln of u. So that's easy. So let's just make u equal to g minus b over m v. And again, I apologize if you're like, what is going on here? This calculus crap stuff, jeez. Anyway, so by doing a u substitution, then we can take the derivative of this, and again, that's calculus, and I don't even know if at this point I can explain, like in calculus speak, why this works. I just remember it, and so that might be something that have you ask your teacher, your calculus teacher. Anyway, the derivative of u with respect to u is du. The derivative of g, which is a constant, is 0. And the derivative of this with respect to with respect to u is, hold on a second here. Yeah, with respect to v, is just b over m dv. This is like v to the 1 power. So if you do that power rule, it becomes v to the 0, which is just 1. And so anyway, that's what's going on there. And so solving for dv, because we want to do, if we change this to u, we have to turn this into u also. So we'll just solve this for dv. dv equals negative m over b du. I just brought this negative b over m to the other side, and you had to flip it. This is dv. And so now we can take this up here and substitute u in, this in for u in for this, and dv in for this, and we get integral of 1 over u and then dv equals negative m over b du. Alright, and then that equals the integral of dt. So we can take constants out. This becomes negative m over b integral of 1 over u du, and this equals integral of dt. Now here's where the difference is at. I'm not doing a definite integral, I'm doing indefinite integrals, meaning I'm not having a a final condition and an initial condition. So because of that, we have to just add this unknown constant in, which that constant would tell us the boundaries, but we don't have that. So we got minus m over b, and this becomes ln of u. Integral of 1 over u is ln of u. And we'll go plus c, and because that's how we handle indefinite integrals. And then integral of dt is just t plus c, another constant. We can combine these c's and just make it 1c over here, because these are unknown constants, so we just make a new unknown constant. We could call it c2, but just to save, save space or whatever, just to make it less confusing, an unknown constant is an unknown constant, so we'll just keep calling it c. If you have issue with that, let me know and I'll try to explain it better. But I'm already at 11 minutes. Oh my god! I'm going to have to hurry up here. Alright. Now I'm going to do something a little fishy, but and I'm going to do it a few times, and it's along the same lines. I'm going to divide both sides by negative m over b. And so these cancel, but what about, is this going to be c over negative m over b? Well, since this is an unknown constant, and even though these are known, I can still combine these, and I could maybe call this again c4, a new unknown constant that has these in it. But again, it's still an unknown constant even with these, and so I'm just going to keep calling it c. Kind of weird, I apologize. So we got ln of u plus a new c, but I'm going to keep calling it c. Whoops, negative, equals negative b over m t. Just a little algebra here, I flipped it to bring it up to the top. Now I'm going to take the e of both sides, e, and when you have an e of pluses, it really becomes e ln of u times e to the c equals e negative b over m t. But e and ln cancel, so this becomes u, and e to the c, again I'm going to do that fishy little old constant thing, is just a constant. I could call it like c27 by now probably, but let's just keep calling it c, and we'll put out here c times u equals e to the negative b over m t. Sorry about this equal, my tablet sucks. Alright, so I was running out of space, so I just changed the size. Hope that wasn't too jarring on your brain cells. So now what I'm going to do is I'm going to divide by c on both sides and do the fishy thing again. U equals c e to the negative b over m t. And you're like, well, isn't that over c? It's just some unknown constant, c to the c28 if it makes you feel better. Then I'm going to take the u that we made way back here and plug that back in. So u equals g minus that. So we got g minus b over m v equals c e to the negative b over m t. So we're going to solve for v, so let's get v by itself. We got b over m v equals g minus c e to the negative b over m t. V equals m g over b minus m g over b c e to the negative b over m t. So you see what I did there with the b over m? I just switched it, multiplied through. And since we've been so fishy with c, why don't we just call c 1? Just for the fun of it, just to confuse you even more. So this becomes mg over b 1 minus e to the negative b over m t. Whew. And so this is what velocity looks like with free fall and air resistance. Let's graph this real quick. And let me pause it. So I'm going to go over 15 minutes. I apologize. I can do that now with YouTube, but I'm going to try to make it as short as possible. I don't want to make 4 videos. Alright. Okay, so I just typed in, I assumed all this equals 1, so I just typed in this stuff here, and v over m is 1. So 1 minus e to the negative x, what does that look like? Terminal velocity. So you start off, here's time, and here's velocity. You start off slow, you speed up, speed up, speed up, speed up, but then you reach a maximum speed and you just stay at that speed. This is called terminal velocity. Here, because we called everything 1, then our terminal velocity is 1. Yeah, so that's another crazy differential equation that you may see on the AP exam. They usually have something like this every 3 or 4 years, and this might be your lucky year. So make sure you learn this, become at one with this at one point. And I apologize, but I'm going to make this video a little longer than normal and do the last concept. You've already done some circular motion in chapter 5, so you're kind of okay with that. But I really want to emphasize from here on that centripetal force is the net force always. It's not a real force. Other forces make it. So for example, if a car is moving around a track, so this is like a top view. Here's a track, a racetrack or something, and you get a car driving around it. It's horrible, but anyway, you got a car driving around. The only thing keeping it moving in a circle is friction. Otherwise, the car would just, even if you turn your wheels, the car would just go in a straight line. And so, moving in a circle, the net force is pointing towards the center, but that's not like there's no magical force. There's no like gravitational force, or there's no rope holding you in. Although there could be, if you were driving on ice and you had a rope tying you here, you'd move in a circle because of the rope. But on a regular road, it's just gravity. I mean, it's just friction holding you in. So you always say F net equals ma net, which is the sum of the forces, individual forces like friction or gravity, whatever. And then you could finally say mv squared over r, where this is r, v is your speed around the circle. Your net force is the centripetal force, and that also equals the sum of the individual forces. So in this case, let's say we only have friction. You could say mu Fn. The force of friction is what's holding you in. And you could even simplify it even more. mv squared over r, which is centripetal force, equals mu mg. M's cancel. And for example, you have the coefficient of friction here would have to equal v squared over gr. It's just an interesting little aside. But anyway, the centripetal force is centripetal acceleration v squared over r times mass. This is F equals ma. F equals ma, which is centripetal acceleration. And just to really emphasize, centripetal force is the net force. The net force. Always right here, this thing. And it comes about from other real forces. Alright, it's a few minutes over, but I apologize, but I didn't want to make a new video just for circular motion. Any questions? Let me know in class. Bye bye.